Welcome. This is the first lesson, or lesson number 2 actually, about forces and Newton's laws. So we're going to start very basic here, and we're just going to ask the question, what is a force, and how do we use them? So a force is a push or pull, and that's measured in something called a Newton. And this is just a measurement of force. It's the unit, kind of like how miles is the unit for, or is a unit for distance. Newton is the SI unit for force. Newton. And we denote it very easily with an N. Right? And this can be push or pull in the sense that, yeah, it could be a person who maybe like pushes a box. Right? And it goes this way, or someone who's even pulling something. But really, it's talking about more of interactions, right? A push or pull. In both of these scenarios, right, we have one person doing something to something else. We have an interactor and an interactee, if those are even words. But a force is a push or pull, right? Another thing about forces is that they, if you have enough of them, can change motion. So forces can change motion. Something we might also use is the words or the phrase state of motion. Oops. And all this really means is that if you have enough forces in one specific direction, you can cause something to change its state of motion. So there are many different states of motion, but I guess the two that are probably most familiar is when we have something that is not moving, something that is moving at some constant velocity, and something else that is gaining speed in a certain direction. We call that an acceleration, right? So we can have this case here or this case here. And if we wanted to change from case 1 to case 2, we'd have to apply a force, right? There'd have to be someone here to move it, to get it going, right? And as it went, if you, again, you can kind of tell, as it goes from stage 1 to stage 2, right? It starts off not moving, and then it moves a little bit faster, and it moves a little bit faster, and moves a little bit faster until it reaches our stage 2. So to get from 1 to 2, that means we do have to accelerate, right? So we're going to talk more about what composes a force. We're going to talk more about Newton's laws a little bit later. All I really wanted to focus on now is how to manipulate forces, and specifically forces in one dimension. And so that brings up this idea of a dimension. What the heck is a dimension? Sometimes we talk about dimensions as us being in 3 dimensions, right? So let's say we have a cube, right? This is a poorly drawn 3-dimensional cube. Well, what does a 2-dimensional object look like? Well, if we take the same one and we went down, we'd just get a little square. And what if we went down then to 1 dimension? Well, we'd have just a line or a dot, right? And this line would go, these are the arrows, now I'm making little arrows, so try not to get confused. I'm just saying that these go in one direction or the other. So 3 dimensions, we can go up and down. We can do that also in 2 dimensions. And I'm going to draw these over here. So in 3 dimensions, we can go up or down. 1 dimensions, we can also go up or down. And in 1 dimension, we can go up or down, but that's the only amount that we can go. We can only go in one way or the exact opposite. In 3 dimensions, in the same way, we can go back and forth. In 2 dimensions, we can do that same thing. And then finally, in 3 dimensions, right, we can also go in and out. In 2 dimensions, you cannot do that. So everything that we experience in our real world, we experience in 3 dimensions, right? We can go up, down, left, right, back, forth, in and out. In 2 dimensions, we could only really move forward or backwards. And then in 1 dimension, you could go either in 2 dimensions, let's start that over again. So in 3 dimensions, you can go up, down, left, right, in and out. In 2 dimensions, you can go up, down, left, and right. And then in 1 dimension, you can only go forward or backwards, right? And you can take these and you can rotate them as much as you wanted to, right? So for example, I could have a dimension that's more just like this, just like that. That wouldn't matter. I could take this, as you notice, this one's horizontal, this one's vertical, right? I could have one that's just diagonal. Doesn't matter, right? You can rotate your dimensions and it's not a big deal because whatever's in the dimension doesn't really notice. So when we go back and we're saying we're going to be focusing on forces in 1 dimension, we're just focusing on this case. We're just looking at forces that either act forward or act backwards. You can say they either act left or they act right, or maybe they either act up or act down. So if I were to define a dimension, I would call it a direction of motion that an object can proceed in. So we can work in 1 dimension, we can work in 2 dimensions and 3 dimensions, but as we increase the amount of dimensions that we work in, the math gets a little bit harder. So we're just going to focus on 1. 1 is pretty easy because in algebra, algebra is actually made to only work really in 1 dimension. When you start working with like the calculus and things like that, you can work in 2 and 3, and it's not too difficult. So we're just going to focus on 1 dimension. So the easiest idea we can kind of do is just like, let's just say there's a box and there are 2 forces. Let's call this one 3 newtons. And call this one, I'll do 4 newtons, maybe it's a little bit longer. I might ask something along the lines of, what is the net force? So you might be asking, what does the net force mean? The net force is some forces on an object. So when we go to our object, we're just going to add those forces up. And the thing is, when we add forces, we have to take into account the direction that they're in. So let's be reminded about vectors. Vectors are physical quantities that have direction and magnitude. And so we have here 4 newtons to the right, we have 3 newtons to the left, right? And so when we add these up, they're really actually going to subtract from each other. So if I was going to write this out, we're working in the x direction currently. So I'd say the sum of forces in the x direction equals, and I'd write my forces out. I have my 4 newtons in I'm going to give that my positive direction, plus a negative 3 newtons, right? Because it's in my negative direction. And that gets us 1 newton. So if I were to sum up all these forces, I would get 1 newton, and that is my net force. So that's pretty easy. And so we're just going to cover 2 more cases. So when they're in opposite directions, they subtract from each other. When they are in the same direction, you can probably imagine that they are going to add together. So let's say we have something like this. We have our same 2 forces. And I might ask, what is the net force on this one? And since they're in the same direction, we're just going to add them. So if I was going to write this out again, let's say sum of forces in the x direction equals 4 plus 3 newtons. And this actually adds in the way that we imagine it to add, 7 newtons. Really quickly, just so you know, this is just a sigma. It just means the sum of. So when I say the sum of forces in the x direction, I'm talking about all of these guys right here. Right? There could be 4, there could be 8, there could be 20, it doesn't matter. So now we've had them in the opposite direction, them in the same direction. What happens if we have them in the same and opposite direction? So let's say we have a force here. So a 4 Newton force. We have our 3 Newton force. Let's say we also have a 3 Newton force this way. What happens then? What is our net force? Well, this one's not too hard. You just add the ones that are in the same direction, subtract the ones that are in the opposite. So this is going to be denoted as our positive, this is our negative. And remember, I get to choose my frames of reference, right? So I'm saying positive and negative. You can actually switch them and you just get a negative answer. So let's say sum of forces in the x direction is equal to, we have 4 newtons for here, so now cross this guy out, plus a 3 newtons, cross this guy out, and then plus a negative 3 newtons, right? And then this guy dies. So that's all of our forces. If we add these all up, we can see that 3 newtons cancel out, and we're just left with a net force of 4 newtons. At this point in time, you might be getting a little confused as to why I have F net and why I have sum of forces. F net is not always going to equal your sum of force. The way that I use this notation is that sometimes I have forces in the x direction, sometimes I'll have them in the y direction. F net accounts for any direction, right? Whereas if I'm working in 2 dimensions or even 3 dimensions, right? Because I could also have the z direction. F net focuses on just whatever direction something is going. So if a box is kind of going at some weird kind of angle this way, where it's like that, your F net's going to give you the angle theta and the magnitude F, whereas these were only going to give you your force in that one direction, right? So just in the x, just in the z, or just in the y. If we're only working in 1 dimension though, F net does equal our sum of forces. And so that's why I've been kind of using them interchangeably, but just try to know that that is the difference. And one more thing just to look at is, let's just say I have another box and one's going up, one's going down. They add the exact same way, right? So let's say if this is like 5 newtons, this is 2, right? You'd say some forces. Now it's in like my y direction, but I mean, it doesn't really matter. If one's in one direction, it's in one direction, right? And make this my positive. We have 5 newtons plus our negative 2 newtons, and that gives us our 3 newtons, right? So up or down doesn't matter. If it's in one direction, it's in one direction. You could keep it the same, right? If we just turned our heads sideways, right, this would just become the same problems that we've been doing up here. One last thing I want to talk about is kind of what I've been doing with all these arrow drawings. So there's something called a free body diagram. Sorry, it should be an A. And this is just how we represent a specific category of vectors on an object. So for example, when we are using forces, we're drawing a free body diagram, we're only really just trying to draw the forces on that object. The reason why we only want to do 1 is because you don't want to get confused and add like a force to like an acceleration. So a free body diagram is how we represent. And for us specifically, I'm going to use forces. So how we represent the forces acting on an object. And they're commonly used or drawn just from a specific point. So for example, this above one here, a lot of people would just draw them like this. And you also try to draw the arrows to scale as much as you can. Right? But sometimes when you have more than one force working in the same direction, it's hard because you want to like draw something like here, draw something like that, and it just gets a little confusing. So it's easier to just kind of draw your object, make it a little bit bigger. You can even make it like a sphere, and that'd just be a lot easier. So that's all I have for you today. Hopefully the math portion of this isn't too difficult, but make sure you finish your worksheet. So thanks, have a good day.